So, who am I? I am a generic web dork. I talk and record about reverse engineering, breaking JavaScript web applications, things like that. I'm director of engineering at Shape Security, Google developer expert. And if you've ever played StarCraft or Fallout way back in the day and broke any of those, you might have been using my tools. Built a lot of hacks for old games, and that's what got me into programming way back in the day. So Shape, first of all, is a name that you probably don't know. Most people have no idea what Shape is. We're not cool like Twitter or GitHub. We're not making games or anything crazy. But have you ever heard of YKK? It's a company that all of you have used their product, but no one knows the company. They make virtually all zippers in the world. You check all your clothing right now, you'll probably see YKK on some of your zippers. All comes from one company. Shape is the YKK of security. You don't know us, but we're everywhere. You've actually probably run code that I once wrote today, and you almost definitely used it when you were getting here. So we are relevant, but we're kind of underneath the surface. We basically make it so you don't see captchas anymore. So, event stream, how it happened. All started with a package, event stream. Event stream was one of the earlier packages created in the Node.js ecosystem that leveraged Node streams. And Node has gotten fairly popular over the years. When you're an early package using part of a core architecture, you're going to explode in popularity. So event stream was just a way to make using streams a little bit easier for people who aren't very familiar with it. So as of right now, it has over 1,500 direct dependents, and as you spiral out from there, it just explodes over time. And it's downloaded over 1.2 million times every single week. So event stream was maintained by developer Dominic Tarr. He creates a lot of code, and a lot of people depend on a lot of what he's written. He's not a no-name developer. A lot of people respect him. He's a good guy, and he does a lot of valuable work. He's got a very, very substantial following, and he writes a lot of code that people depend on, hundreds upon hundreds of repositories and packages. And one day, last year, September of 2018, he gave this package, event stream, to a random person. Now, why would somebody do that? A lot of people who develop open source have a dream of someday having a package that gets remotely close to as popular as event stream. Why would he give something like that away? And luckily, he actually just posted why he did that online. And the gist of it is, he didn't want it anymore, and somebody asked for it. And that's okay. When you release code online, you shouldn't be expected to maintain it for the end of time. It's fun at the start, but eventually it starts to suck a lot. And for somebody who has hundreds and hundreds of repositories, if you get somebody who wants to maintain one, it's like, yeah, sure, absolutely, take it, please. And that's what happened here. So Write9 Control started to make some relatively innocent changes. Updated dependencies, event stream hadn't been used in a while, normal stuff. Added some documentation, added some examples, all stuff that looked very normal for somebody maintaining a package. Nothing major, nothing that would draw attention. And then on September 9th, 2018, Write9 Control added a new dependency, flatmap-stream, and then released version 3.3.6 of event stream. So about that carrot. Everyone know semantic versioning? Should. This is the room that should know semantic versioning in a talk like this. But for anyone who's not entirely up to speed, semantic versioning is the number versioning scheme that a lot of projects use and is very, very prevalent in node-based projects. The numbers are supposed to decrease in risk. So as your patch version increases, it should just be bug fixes. As your minor version increases, it should just be features that don't affect the core functionality of what already exists. When you bump a major version, that's when something changed, and you have to be more wary about it. So semver pattern matching is for basically the ease of updating dependencies. The caret and tilde means something special to NPM, and when you specify a dependency by using a tilde or caret, you're basically saying, I'm okay with updating these dependencies as long as it falls within this range of risk, which is generally a good thing. Mostly updating dependencies is something you want to do, and if it doesn't break anything, that's good. Unfortunately, though, with what we're talking about, updating dependencies all the time comes with a lot of problems. So write9 control then removed flat map stream and then released event stream 4.0.0. Now a note here, nothing malicious has emerged. This is all looking relatively normal, and even the last removal of flat map stream and the update, that also seems kind of normal. Exposed the new API, then realized didn't want to expose it, removed it, updated the major version. That's not crazy. So time between first commit and version 4.0.0 was 12 days. So on October 5th, 2018, 31 days after ownership changed in Event Stream, a new version of Flat Map Stream was published, 0.1.1. Event Stream 336, installed fresh now, pulls in this updated dependency because of that caret. Event Stream 335 was stable for 2+ years, and a lot of things depended on Event Stream with a caret 335. So as soon as anything that depended on Event Stream basically in the world updated or installed dependencies fresh, it would pull in that updated flat map stream dependency. So the time between malicious control and discovery was 77 days. Time between flat map stream 0.1.1 and 0.1.1 and discovery was 48 days. So 0.1.1 was the first introduction of malicious code and was in the wild before anyone noticed for over a month and a half on a project that was downloaded 1.2 million times a week. I think it was about 8 million developers downloaded this package over its lifespan. So first off, what did it do? First, how actually did it how was it discovered in the first place? This entire story is one of those things that's just fantastic because it's like a Hollywood setup. Everything works so well and plays so nicely off each other. So the first payload in Flat Map Stream used a method that was deprecated in Node 11.0.0. It was deprecated in version 10, but it was just documentation deprecation. As soon as 11.0 hit, then you started getting a console log or a warning in the terminal. Node 11 was released 18 days after FlatMap 0.1.1 was released. So now unrelated projects started to get warnings of this deprecated method. That deprecated method was a method in the crypto library. A lot of projects shouldn't be touching crypto libraries. So this was a warning that started to raise some red flags, and eventually Falling Snow opened up an issue on Event Stream, basically wondering what the hell's going on. Something weird is going on. It looks like there's this malicious dependency. I'm getting a warning in NodeMon. This doesn't look right. So how was it discovered? Dumb luck and coincidence. There's no reason this would have been discovered otherwise had there not been that warning. It had already been lying low for a month and a half, and even piecing it together at the end required some work. If people just updated the event stream dependency to 4.0.0, that warning would have gone away. And I think that's probably what the actor was hoping for by releasing it that way. People would just get past something like that, and they would just move on, and you wouldn't have to worry about that dependency. So FlatMap Stream 0.1.0 looks like this. You also notice something weird at the start. It's a Node.js dependency. It's minified. That's actually just something that we as a community have gotten used to. It's normal. You download distributables, and they might be minified. It might be all sorts of weird transpilation artifacts. So we're already looking at code that we can't really easily read. FlatMap Stream 0.1.1 just looks like this. It has 352 bytes added to the end of it. This is the first payload. So payload A, this is the bootstrapper. This is what runs in order to enable the rest of the payloads. This is what it looks like prettified, cleaned up a little bit and flattened, and removing some of the fluff there. It looks like this. So at the start, we have a function that I've renamed unhex because all it's doing is taking a hexadecimal string and translating it into something that you can read. The first thing that actually runs here is an unhex on just a literal string inside the code. We can do that by hand, and we can see that it is requiring an external file called test/data.js. This was present in the malicious payload and is just a list of strings. So these are all the hexadecimal strings. The first two are very, very large. I've cut them there. When you try to unhex them, you just get binary data. They're not that useful for us right now. The rest of the stuff, though, is pretty useful to see. You get crypto, you get NPM or NPM package description, env, AES. You can tell why the actor wanted to obfuscate this stuff, because if you saw these literal strings in random code, it would set off some warning flags right away. So after rewriting payload A and shifting out or replacing some of those strings, we get this code, and we're going to go through it line by line. First step here, what we already went over. We're importing test data and into a variable called test data, because why not? Next step here, we are getting something from the environment, npm package description, which is the description from the package.json, and we are using that as the key to create a decipher instance. Next step here, we are decrypting the first element in test data. So those big strings I was talking about before in the test data file, we're decrypting that first string there. Next up, we're creating an instance of a Node.js module, ignore the past thing, and then we are taking the decrypted data and then using that as the source for this module. And then we are exporting from that module the second element in the test data. So going back to this top up there, we can't do anything else unless we find this key. This one's an important one, and we're not going to be, well, I'm not going to be going through and brute forcing what could be a massive, massive range just to decrypt this. This was just one of those fun little things I saw when it was happening, and I was diving into it. It was very, very easy for it to drive me off track, because reverse engineering stuff like this very rarely goes smoothly. You get to a point where you understand the gist of it, and you move on, and you mitigate the problem. So here, for anyone who, this is an unrelated package JSON. So for anyone who's not entirely familiar with the depths of NPM, it obviously manages your dependencies, but it also is a task runner. If you've ever used it to run tasks, they are defined in the scripts portion of the package.json. They look like this. They are just keys in a scripts property and then a list of commands that you run. So this is how NPM runs scripts, and when you run a script via NPM, it pulls in all this data from the package JSON and puts it into the environment. So what we're looking for here is an NPM script that has a description that can be used as a key to decrypt the first element in that test data. So to recap, this script decrypts and compiles a new module. That key to decrypt that module comes from a package description somewhere in the world. That encrypted, the JavaScript comes from the first element, and then it exports the second element. So what this means in plain English is that we need to find, this script will only do what it needs to do if it is run as an NPM script in a directory that has a package JSON that has a description that will properly decrypt that first element. So what this means for us is that we need to go through a ton of package JSON files. Now, where do you get the largest repository of package.json files? You go to NPM. And luckily and conveniently for us, there is a package called all the packages, which allows you to consume the package metadata as a stream and go through it one by one. And yes, of course, it depends on event stream. So when you're dealing with malicious code, stuff like this, and you're trying to investigate, you probably shouldn't be doing it on your main computer, because we don't know what this code's doing. Might be very, very malicious. Chances are, though, that we've all already run it. We're already in a problem state. But just in general, virtual machines and burner laptops are useful. So the strategy through here is to iterate through every single package that exists in the NPM registry, use the package description to decrypt that data, because we know that the decrypted data is being passed to the compile method of a module instance. We know that it has to be JavaScript. Because keys can decrypt data and just end up with other gibberish, we're going to want to take that decrypted data and run it through a JavaScript parser just to make sure it parses as JavaScript, so we don't have to do anything visually or by hand. Now, this is the type of Hail Mary that very likely is not going to work. This is just the first obvious place to go in order to see if we can get some clue as to what is actually decrypting this, this file. After 20 seconds, the password pops up on the screen, and it was almost just like one of those those amazing experiences as a security researcher, because now you unlock the rest of the experiment. You get to keep on going. And that's what I mean, this is Hollywoody. It's like almost everything was linking together and allowing you to keep going. Now, of course, it's targeting Bitcoin, because what doesn't target Bitcoin at this point? It's relatively unexciting to me, because I would expected something more beautiful. This was targeting the Copay Dash wallet, a secure Bitcoin wallet for you to keep all your fancy crypto. Probably shouldn't do it anymore, though. Probably should move to a different one. But now this means that we could also now decrypt the next stage. So the first stage was the bootstrapper. The second stage is what's going to inject the final stage into its destination. This is what we're looking at right here. We don't need to go through this line by line. It's doing a lot of the same stuff, but there are two things to focus on. The first line here that gets executed is testing something in the execution against a regex. If that regex doesn't pass, then the script doesn't do anything. So we already know that we're targeting a very specific package JSON, and now we're targeting a very specific way of running this. So it's looking for the the second argument to a command on the command line. We already know that we are being run as an NPM script. NPM scripts are run as npm run-script, the script name. So what we are looking for here is the script name that is going to be targeted. Now, because Copay, oh, not quite yet. So this particular regex is looking for build::blah-release, because Copay Dash is luckily an open source application. We can look at the package JSON that was being targeted. Now you can see here there's build::iOS-release and build::Android release and build::desktop release. If you're familiar with the history of web development and native applications, you'll also recognize Cordova. Cordova, for those of you who aren't familiar, is PhoneGap by a different name. Basically a hybrid development environment that allows you to use web technology, HTML, CSS, and JavaScript on native applications. So we are targeting the build step for Copay Dash's application being built by Cordova. So this next line here in payload B is poking deep into the dependencies of Copay Dash in order to find a file that it knows Copay Dash will hydrate and run in a context that the script wants to be run in. So this is not a malicious dependency. It's just a random file that is depended on by Copay Dash. So to recap, payload B doesn't do anything unless we are being run in a very specific build stage of Copay Dash's application. It decrypts payload C the same way that payload B was decrypted, and it injects payload C into a dependency of Copay's mobile application, and then payload C is then executed in the mobile application context on a mobile user's device. Payload C, the final payload. It was all I could do to not put a reference to Europe in there. So payload C is this. It's a lot longer. We're not going to go through it, but it's the final payload. And the final payloads of a lot of these things are usually the least exciting. It's everything that gets you to where you want to be that's exciting. The code at the end is just doing what you wanted to do in the first place. This is just standard web code. There's some document stuff, local storage stuff, Ajaxy stuff. The gist of it is it was harvesting private keys. It was targeting wallets that had at least 100 Bitcoin or 1,000 Bitcoin cash, and it was sending all this data up to a third-party API server. So, where does this leave us now? This is not Node and NPM specific. I know that you all are probably perfectly okay believing that, but for everyone outside of this ecosystem who points at us and be like, ha, you're a bunch of slobbering jerks who do horribly insecure things and tear the world apart, you can point to them and say, no, this is actually a problem everywhere. We're just more popular than you. That's why things like this happen. So the good news is that as soon as this came to light, the community rallied around it instantly. You had a bunch of independent researchers. You had people like me who reverse engineer things, and as soon as they saw this, they dropped everything and tried to focus on it to see what was going on. And then once it was found out, people were notified. Tools were written in order to make sure that it was mitigated, or you were able to detect whether or not it affected you, and if it did, to mitigate whatever that effect is. The bad news is that it happened literally again this week. If you've read your NPM weekly or Node weekly, whatever it was, you'll see that NPM it mitigated themselves this problem for another Bitcoin wallet. But the problem is that it was the same exact type of attack. It was the exploitation of a dependency that was automatically updated and was sucked into a target application, and it did whatever it needed to do to get what it wanted. This whole thing could have been much, 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 much worse, just in general. Event Stream was downloaded all over the world, all over the place. And I have to imagine that the target was obviously determined in advance, and as soon as the route in was found, the target was just what was focused on. Everything else was on the side. The scope of exploitation here was so amazing, though, that I have to imagine the actor probably regrets only targeting such a small sliver of the world. This was depended on by the Azure CLI, so anyone who was using the Azure cloud platform had potential to be exploited. So anything that you were deploying there had potential to be infected. Dozens of build tools, basically everything Gulp depended on Event Stream. So anything that was built by Gulp had the opportunity to be infected. And the code editor, Monaco, for Visual Studio Code depended on Event Stream. So you didn't even have to be bought into fully the Node.js NPM ecosystem. You just had to use Visual Studio Code, and you might have had this problem arise somewhere else. This was widespread, and I guarantee that basically every single one of us here had this malicious code on our computers at some point. This is likely, as a problem, going to get much, much worse. There's a lot that needs to happen in order to make sure that this never happens again. But unfortunately, these are hard topics that require lots of changes, lots of buy-in, lots of backwards compatibility concerns. And every time those things come up and an opportunity arises to kind of just step aside and let it fall to the floor, people will let it fall to the floor because these are hard conversations. There are some conversations by important people talking about some strategies to evolve platforms in the future. One of the ways around that, Ryan Dahl is exploring with Dino. So Ryan Dahl is the creator of Node a long time ago, regrets some of the things that are in Node now. Some of them are his choices, some of them are other choices. In general, there are things that he would have preferred to do differently now. He's experimenting with some of those concepts in Dino. One of those concepts is privileged API access. The same type of things that we use on mobile phones. Like you download an app, you say, I allow this app to use GPS or whatever else, it uses GPS. If you say no, can't use GPS, or you don't download the app, something like that. You could do that with a lot of APIs that are accessible in Node. I/O access, crypto access. If you're using dependencies like LeftPad, they shouldn't have access to all these things. So stuff like that is baked into Dino. So what can you do now? First off, rethink dependencies. Audit your dependencies, lock your dependencies, check in your dependencies. And I know I'm pissing people off with some of these, and I'm sorry. Think twice before adding any new dependency. When in doubt, don't add it. Every dependency you add is risk you're adding to your application, to your company, to you. And risks are gambles. You only take a gamble if the cost is lower than the value. And if the value is high, then it's worth taking. If the value is low, then you were just putting yourself at risk for very, very little value. And if you make those gambles over and over and over again, you're going to find yourself in pain. So, thank you very much.